recurrence relations, or as you might see them called, recurrence equations. And these are related to, and sometimes they are called, difference equations, very similar. So I want to start by just going through some recurrence relations or recurrence equations that we might be somewhat familiar with. So let's start with the Fibonacci sequence. We have f0 is 0, we have f1 is 1, and then we have that fn is f of n minus 1 plus f of n minus 2. So that's a very common example. Another common example, maybe not common, but another example that we've seen something like this in this class is the number of ternary strings of length n without the string 0, 0. Well, how do we do this? Well, let's say t of 1, the number of ways to get a 1-length string is going to be 3, because it can be either 0, 1, or 2. T of 2, the 2-length string, is going to be 5, because it's any 2-length string, 2-length ternary string, except for the string 0, 0. And then to get the general form, we have the string of length n. Well, if it starts with a 1 or a 2, so it's two choices, we just have t of n minus 1. If it starts with the 0, or if it starts with a 0, then the following ternary digit has to be a 1 or a 2. So two choices. So it starts with a 0, then it's a 1 or a 2, and then we're just 2 steps down. We're looking at t of n minus 2. The next example I want to do is, again, something that we saw earlier, and this is the number of regions in the plane described by n intersecting lines. And we've already seen this, but the basic idea was if we have 0 lines, we have just one region. Let's do this over here. If I draw a line in the plane, now I have 2 regions. And in general, at step n, when I have n lines, I'm taking the previous result and adding n regions. So I had 2, then I added 2 more. Now I have 4. When I draw another line, I've got to cross all the previous lines. So I'm going to add 1 region for each line that I cross plus another region. So I crossed 1 line here, crossed 1 line there, and each of those lines serve as dividers between the new regions. So 1, 2, 3 new regions. If I draw a 4th line that crosses these 3, I have all the previous regions, and then there are 3 lines dividing the 4 new regions. So in general, we have L of n is L of n minus 1 plus n. So these are different types of recurrence relations or recurrence equations, different examples. And now I want to sort of characterize these and give some nomenclature to these. So the key terms that I want to talk about, we're not going to do a whole lot with these terms, but we're going to use these terms, are linear recurrence relations or recurrence equations, and also homogeneous. So I'll make this a little bit more formal in a second, but initially I just want to say that a recurrence relation is linear if I can get information about the nth term in my sequence by looking at a linear combination of previous terms. For example, I don't have fn is a product of fn minus 1 and fn minus 2 or something like that. So it's just, I've got constant combinations of these previous terms. Again, and that's to say nothing of the initial data, but the sort of the recurrence relation part, it's a linear combination of previous terms. Here, linear combination of previous terms. Then these first 2 examples are going to be what I call homogeneous because it's just combinations of the previous 2 terms, of previous terms, and not any other expression. However, the regions of planes described by intersecting lines is not what I would call homogeneous, because we have this term here, which is not explicitly a previous term. So I'll say that a recurrence relation or recurrence equation is linear if it is a linear combination of previous terms and so I guess this would still be linear because we don't have the previous terms multiplied together or something like that, and possibly other functions. It's homogeneous if it's only involving previous terms, no other functions. And these are not super rigorous terms, but these are just terms that I'll be using for us moving forward.